Let us study about recoiling of an atom during de-excitation. We have studied that if we talk about a hydrogen-like atom or even a hydrogen atom, in which say an electron makes a transition from N2 to N1. In this situation, this hydrogen atom emits a photon which will carry the energy which is equal to the difference of the electron energies for the two corresponding energy levels. Now, when the photon is emitted, as we have discussed that photon also carries some momentum. Due to the ejection of this photon, the hydrogen atom must recoil with a recoil speed Vr in opposite direction, because if initially the hydrogen atom is considered to be at rest, final momentum of system must be zero. And if a photon is emitted with some momentum, then hydrogen atom must recoil to compensate the momentum, so that total momentum of system must remain zero. In this situation, say if the photon emitted is of wavelength lambda, then in this situation we know, as we have studied in previous sections, that momentum of a photon associated with it can be written as P is equals to h by lambda. And if hydrogen atom is of mass mh, which recoils with the speed Vr, then we can say by conservation of momentum, initial momentum was 0, so finally the two momentum in opposite direction must be equal, then only the final resultant momentum will be 0. By conservation of momentum, this implies mhvr must be equals to h by lambda, that is the momentum gained by the photon in leftward direction must be exactly equal to the momentum gained by hydrogen atom due to its recoil. Now in this situation we can directly calculate the value of recoil speed, that is h over mh lambda. Now in this situation the value of lambda we can calculate by using Rydberg's formula. By Rydberg's formula, which we have studied in the previous topic of atomic structure, this Rydberg's formula says 1 by lambda is equals to r z square 1 by n1 square minus 1 by n2 square. That is for a hydrogen-like atom, and the value of 1 by lambda, if we substitute here, this will give us recoil speed Vr is equals to, this will be h over mh lambda, 1 by lambda. If we substitute, this will be hrz square by mh multiplied by 1 by n1 square minus 1 by n2 square. This is the recoil speed we are getting using this relation, and this will be approximately correct. The only difference in the value calculation here is we have supplied the whole energy emitted to the photon, and we have calculated the photon wavelength by using Rydberg's formula. But in actual, we can see the amount of energy which is released in the transition will be shared by hydrogen atom as well as that of the photon. Hence, in actual situation, the value of wavelength of which the photon is emitted will be slightly more than this value what we are calculating, because in this expression we have considered that whole of the energy of transition is taken up by the photon. So this will be approximately correct, but for numerical analysis this can always be taken. The slight difference, if we wish to account expressionally, let's continue on the next sheet. Let us reanalyze the situation of recoil of hydrogen atom. But in this situation, we'll consider that the electron energy which is released during its transition from N2 to N1 will be shared by photon energy as well as the recoil energy of this hydrogen atom. Whereas in previous case, we have taken the photon wavelength to be lambda, and the whole of the energy released by electron we have supplied to the photon. In that situation, there was a slight error in calculation of this Vr, because in that situation energy will not be perfectly conserved. But numerically the error is negligible, so we can consider that analysis well for a different kind of numericals. But for exact analysis, Here we can say water amount of energy is released by electron. This is given by hc by, instead of lambda we write rz square 1 by n1 square minus 1 by n2 square. This is the total amount of energy released, which can be written as the sum of the two energies. One is that of photon, which is hc by lambda prime, plus the kinetic energy of hydrogen atom, which is half mhvr square. This is the recoil kinetic energy. Here lambda prime we can write it is slightly more than lambda, which we have calculated in previous case, because some energy is shared by the hydrogen. So in this situation actually the photon energy will be slightly less, so wavelength will be slightly more. And we can write also by conservation of momentum, we can write as initially this hydrogen atom was at rest, so final momentum must be 0. Here we can write mhvr is equals to h by lambda prime. Using these equations 1 and 2 we can directly get the value of lambda prime. Here I just leave it as an exercise for you to calculate lambda prime as well as the recoil speed. So here we can write using 1 and 2, after solving we will get the value of lambda prime as well as we get the recoil speed of hydrogen atom. So these are the values which are the actual values of emitted photon wavelength in this situation and the recoil speed of hydrogen. Here we can also write one thing that if hydrogen atom were kept at rest, it was rigidly fixed, then the emitted photon will have a wavelength lambda only, because no energy will be taken up by the hydrogen atom. So conceptually you must be very clear with this. I am leaving these values to be calculated as an exercise for you using these equations.